Hello and welcome to question 2 on this worksheet. We're clipping along on this worksheet. No, 45-minute explanations of a single part of a question like we had last time. So now we're going to talk a little bit about runtime of binary search trees and certain operations. Now, thing to keep in mind here is we're talking about the best and worst case. We're not talking about theta bounds or anything. So keep in mind that in some cases, we're kind of going to short circuit to a best case. And you'll see what I mean when we talk about this. So basically, we're talking about the best and worst case notation in theta for various operations of binary search tree. If you don't understand why best and worst case is described in theta and not like omega and O, you can watch like my last video on asymptotic analysis from last week's worksheet 6, which is very long and very detailed and all of that stuff. So I hope that clears things up. So basically, we're talking about binary search trees. So let's talk about how binary search trees work. So we know, of course, that with a binary search tree, you basically put elements in, and then if you put an element that is smaller than the key you're trying to put in, you put it to the left. If it's bigger, you put it to the right. So you might end up with something like this. But there's lots of different ways you can end up with a binary search tree. So if you put in nodes in the order 4, 2, 3, 5, you'll end up with something like this, right? You'll start with 4, then you'll go to 2, then you go to 3, then you'll go to 5. But if you put things in the order, for example, 2, 3, 4, 5, well, what will happen? You'll start with 2. Whoops, you'll go to the right for 3, to the right for 4, to the right for 5. Notice that these binary search trees have the same number of elements in them, yet this is a depth 2 tree and this is a depth 3 tree, right? In other words, binary search trees do not balance. They don't necessarily give you the most optimal way to put keys in a particular binary search tree. They're entirely dependent on the order in which you insert the keys, which is going to be good and bad. And we'll talk about that a little bit more in the rest of the worksheet. It's good because it's simple. It's bad because it gives you bad runtime. So basically, you can imagine a binary search tree that ends up looking something like this, where every node has exactly 2 children. In other words, it's kind of a full binary search tree. We refer to this as a bushy tree, right? It's like it's got a lot of leaves, it's not drought ridden. And then you can imagine another situation in which we have a tree like this, where just like in the tree I drew, when you inserted things in increasing order, in this case, this would be something if you inserted them in decreasing order, you get a tree that is what we would call spindly, meaning it has a lot of nulls for its children, right? Notice that none of the right children are filled here. Notice that this tree is actually deeper than this tree, yet this tree contains 7 elements and this one only contains 4. And you can imagine how much longer it gets if you start, going to a point where all of your elements are spindly. Okay, this will also be relevant when we're talking about best case and worst case in binary search trees. So in general, you can see that if we have to traverse a spindly tree, it's going to take n time, right, to get to the deepest node because we have to go through every other node to get there. Whereas if we want to hit one of the deepest nodes, say this node in a bushy tree, it's only going to take log n time because we can store more nodes as we get deeper and deeper. Okay, so keeping this in mind, we can basically start looking at these questions. So let's say that we want to run contains on a binary search tree. This is just a general binary search tree. It can look like this, it can look like this, it can look like anything in between. And we want to know what is the best case, why, what is the worst case, and why. So in contains, all we want to do is scan through the tree, usually with one of the algorithms we did in the first part, BFS or DFS, and figure out if a particular element is in that tree. So what's the best case with this? So you might say, oh, it's log n because if your tree is bushy, then it's, the minimal search distance, but it's actually a little bit of a trick question. This is actually constant time because the best case is just that the element you're looking for is the first element, right? Because once you find the element, you can stop searching, right? If the element doesn't exist in the tree, then yes, it would take log n, right? For example, if you search this binary search tree and you were searching contains on an element that you knew did not exist, it would take log n time because you have to search every node. Actually, that's not necessarily true. I take that back. Depends on how you sort it, but it can take up to log n. But in general, if you find it on the first go, it's going to take a best case of constant time. Okay, but what is the worst case? Well, the worst case is if you have to go all the way down to the bottom of the tree. Let's say you have that tree where it's 5, 4, 3, 2, 1, and you want to run contains on 1, well, you have to go through 5, 4, 3, 2, 1. So it will take up to n time, and that's why. I'm not going to write the justification down because I'm just going to say it. But best case is basically you find it in the first go, and worst case is you have to go all the way down a spindly tree to find it. Okay, insert. How long is it going to take to insert something? Okay, so this one is also a little bit of a weird trick question too. So what is the best case to insert something? Well, again, you might say, well, if we have a bushy tree, this is kind of the optimal BS tree or BST. So if we want to insert something, it would take log time because we have to get down to here and then maybe insert it here or insert it, here or whatever. However, look at the spindly tree. Again, let's consider a tree where we have 5, 6, 7, and let's say we're going all the way down. We go, 6, 5, 4 into the negatives. We have a really long tree of length n. Okay, and now let's say, oh, I'm dumb. Sorry, I drew this the wrong way. 5, 4, 3. Sorry, the lesser on that side, etc. We're going all the way down to the negative numbers. Okay, so now let's say that I want to insert 10. How long does it take to do it? Well, it just goes right here. So actually, this is a constant time operation. So this is kind of weird, right? Because the best case for insertion actually happens when you have a spindly tree, which is generally the worst case for like a contains operation. So having a bushy tree is not necessarily advantageous in every respect, and this is an example where it's not. Okay, sure. What is the worst case? The worst case, I think, is a little easier. The worst case is just when you have maybe that tree of 5, 4, 3, 2, and you want to add 1 at the end. You have to traverse all the other nodes, just like in our contains operation. That's going to take n time when you have to go all the way down the spindly tree. Okay, get element. It returns the smallest object in the tree. So one thing here is that to notice is that get element is really just the same thing in contains as contains. In contains, you just search through the tree for a given element and you return true if that element is there. And in get element, you're going to search for the tree through the tree for a given element, and you're just going to return the element rather than true or false. So this is actually just going to have the same runtime as contains because it's basically the same thing, except instead of returning a Boolean, you're returning the actual object. So for the same reason that the first one is constant and n, this one's going to be constant n. But just to re-explain it again, the best case is when you immediately find that element, it's the first element of the tree, and you can just return it. And then the worst case is when you have a spindly tree and you have to go all the way down and return the element at the end of the tree. Okay, so that's that question. I hope this has been useful.